So in this demonstration, we're going to start by looking at the significance of the p-value and how we can use the p-value to determine whether our result is credible or not. I'll then go through two worked examples, one using non-correlated data and one using data which may or may not be correlated. The last part of the demonstration will just cover how to make combination charts in Excel. This is where we can get two different chart styles on the same graph. So let's turn to the significance of the p-value. In the previous practical and the demonstration, I showed you how you could calculate a p-value, and this p-value was based on your r-value. And the r-value was telling you something about the correlation between two datasets. So just remember that this p-value, when we're looking at correlation, is telling us how unlikely two sample datasets are related. So in layman's terms, if you have a p-value that is 1 or near 1 in value, there is no correlation. Whereas if you have a p-value which is 0 or near 0, you have a perfect correlation. Any value between 0 and 1 is somewhere within that range. So commonly in science, we use the p-value to work out whether we can trust the results in our data. In this case, whether we can trust that the r-value is telling us that the correlation is there or not. We commonly set an arbitrary threshold, and this threshold tends to be 0.05 for the value of p. So what does this actually mean? Well, simply put, if your p-value that you obtain is below the 0.05, then your result is considered to be significant. Therefore, you can trust that result. While any value below the 0.05 are deemed to be not significant, and therefore shouldn't be used. So this is the first of our fully worked through examples. On this worksheet, I have some data. In column A, we have latitudes on a planet. In column B, we have the diameter of craters at these latitudes in meters. So what we need to do is threefold. The first, we need to work out whether our data here is parametric or non-parametric. We then need to work out whether this data is correlated, either by using the Spearman's rank or the Pearson's, depending on whether it's parametric or non-parametric. Once we have an r-value, we need to calculate the p-value, and the p-value will tell us whether we can actually trust the result of the r-value. So how do we go about this? Well, the first thing we want to do is work out whether our data is parametric or non-parametric. And the easiest way in Excel is to do that visually. So what we want to do is plot a histogram for our latitude data and a histogram for our diameter data. We then just want to visually compare those two. Now, because we don't know how many bins we want, because this data is quite random, what I'm going to do is calculate the bin width automatically, or at least semi-automatically. And this is what this little table up here is for. So the first thing I want to do is work out what the minimum value is in my latitude. So I'm going to use the min function. Select all our data, close the brackets, and press enter. I'm going to then work out what the maximum is for our data, and that's with the max function. Again, select all the data and close the brackets. I'm then going to calculate what our range is, and this is simply the maximum minus the minimum. So we now have our full range of data for our latitude. Now where I've got bin hash here, this is just the number of bins I want to create. I'm going to say I want to create 10 bins. Now to calculate our bin width, and this is simply our range divided by our bin number. In this case, we end up with a bin width of 13.4. Next, we need to use this data to calculate our bins and our frequency data. Now we want to have our 10 bins here and then our frequency data for each of those bins in the next column. So how do we use this data we just calculated to create this? Well, the first thing we want to do is take our minimum value and we want to add our bin width to it. This gives us the position of our first bin. Now what we then want to do is drag this function all the way down through our table and just auto-populate the results. However, if I was to do that to start with, I would also be dragging down this particular value here and also our minimum value up here. So how do we get around this? Well, the first thing I want to do is lock our bin width as such. And then I can just drag this down. Now, as you can see, it's still not working. And the reason is that we've actually moved our minimum value down to our maximum value over here. Now, there's nothing we can do in locking to solve this problem, because we don't want the minimum value to be our reference here. What we actually want is to reference our previous value above. So here, I just need to change our reference. So now every time we drag down, what we'll be doing is taking our value from the bin above and then adding our bin width to it. Now I can drag this down. And as you can see, it's auto-populated all our data up to our maximum bin value. So the final thing to do before we produce our first histogram is just to fill in this frequency data over here. And to do that, we come over, press equals, and start typing the word frequency. Bring up the frequency function. It's asking for the data array, and that's our latitude data. We select that. It then asks for our bin array, and they're the bin values we've just calculated. So we put that in, close the brackets, and press enter. Now, as you can see, Excel has automatically filled in the rest of the column and put all the row values in for us, including this extraneous 0 at the bottom, which as previously we're just going to ignore. We can now create our histogram. So I'm just going to select our frequency data, come up to our insert, come over to our 2D column bars, click on that, and we now have a frequency chart, or our histogram. Now you can refine it, and you could change all your labels on the bottom here, so these would actually be your bin values. If you want to do that, you can go up to your select data, choose your horizontal axis, press edit. Now we just want to select our bin values over here as our labels. Come back. We now have a histogram with our actual bin values on. Say OK, and that is the first of our histograms. Now I'm just going to change the title so it mentions latitude, so we don't get too confused. I just call it lat histogram. Now the next thing to do is follow the exact same procedure, but do it for the diameters. So we want to work out all this data for the diameters, then work out our bins and also our frequency. Finally create another histogram. Now using the magic of video, I'm just going to skip ahead at this point, and it's going to magically appear on your screen. So here's our data after I've calculated our second histogram. And our second histogram is down here. Now the first thing you should notice when looking at both these histograms is that neither of them are looking particularly bell-shaped. And we're looking for that bell shape of a normal distribution to tell whether it's parametric or not parametric. Now this top one here, you might be able to imagine there's a slight bell-shaped curve here. However, there's a big dip in the center. If we come down to our diameter data, you can really see that there is no bell-shaped curve along this graph. This is most definitely non-parametric data. So for this reason, we would have to use the Spearman's rank correlation rather than the Pearson's. And that's what we'll now do. So over in this little table here, we've now decided that we are using the Spearman's rank and not the Pearson's. So, what do we do to calculate the Spearman's rank? Well, the first thing we need to do is rank our data, and that's what these two columns over here are for. So as previously, we would then do equals, start typing the word rank, choose the rank average. The number it's referring to is our number over here, the one we want to test. We then want to have our reference, which is all our data in our entire series. We then want to close that. Now before I drag this down and fill in the rest of the gaps, I just need to lock our range for our data, because I don't want that to drag down as well. However, I do want our A2, which is the value we're testing, to move. Once I've done that, I can drag that all the way down, and then we have all our ranked data. I just need to do exactly the same for our diameter. So again, rank average. This time I choose the diameter value to test. I put a comma in, and then I choose all our diameter data. Make sure that is locked. Close the brackets, press enter, and now I can just drag this down. We can then come over to our little table here, where I said correlation, R value, and we can use the correl function, so the correlation function. So our array 1 is our newly created latitude, but ranked, and our second array is our diameter data, but ranked. Put both of those in, close the brackets, and press enter. We've now got our R value. In this case, it's minus 0.08, so it's very near 0. So that's telling us that we are not very correlated. So the next thing we want to do is get our p-value to find out whether this value up here can be trusted or not. So we need to calculate our t-stat value. So in this cell, I'm going to start typing our equation. But I'm going to alter it just a little bit, and this is because we have a negative correlation value. And this equation to calculate the t-stat really only works well if we have a positive R value. So what I'm going to use is the absolute function to start with. And this just removes any negative symbols from our number. So it turns negative numbers into positive numbers. I'm then going to, as before, square root with the square root function our count. So this is the count of all our data, minus 2. I'm then going to divide that by the square root of 1 minus, and again I'm going to change the function just slightly here and have the absolute R value, and that's going to be to the power of 2. So the little hap symbol, which again is Shift 6 on my keyboard, 2, close that. I can then close the brackets again and press enter. So that's our t-stat value. And the final thing to do is calculate our p-value. So in this cell, I'm just going to start typing our t dist 2t for our two-tailed student distribution test. I'm going to put our x value in, which is our t-stat value. I'm then going to put our degree of freedom, which is the count, again, of all our cells, minus 2. And then close the brackets and press enter. And this is our p-value. Now, as you can see, our p-value is 0.64 and then a load of other digits. The important thing to note is this is way above our significance value of 0.05. So what does this tell us about our result and our R value here? Well, it tells us that we have no significant result, so we cannot trust this R value. And the R value itself is just telling us that there's a very weak negative correlation. So now let's move on to our second fully worked example. This time I'm using a slightly different data set. We have column A, which is lengths in millimeters, and a second data set of widths in millimeters. The only other difference is that we have slightly more data. So we now have 75 individual data items and values. The rest of this table is set out in exactly the same way as in the previous example. Now, I'm not going to sit here and make you watch me go through and calculate all our minimum and maximums and our bin widths, nor am I going to go through and demonstrate how to calculate the bins and the frequencies again. This is going to be exactly the same as in the previous example. So I'm just going to skip ahead to what it looks like once we have our two histograms on screen. As you can see, I've now plotted the two histograms, one for our length data and one for our width data. So the next question to ask ourselves is this data parametric or non-parametric? If we look at our two data sets, we can see that we have a more bell-shaped curve present. And this is in both data sets. However, it's not completely normalized. We do have a central peak, but the tail on our right-hand side is longer than our left-hand side. We're also missing some frequency data around the 7 and 8 bins. With our width data, we have more changes in the peaks in our frequency data than we would like. And similarly, our tail on our left-hand side is slightly shorter than our right-hand side. So this data probably isn't parametric. However, it is quite hard to tell. It's very close in terms of the bell-shaped curve that we are looking for. So for this example, I'm going to calculate both the Spearman's and the Pearson's value for R. This will allow us to compare the two and just see whether there's any massive difference between them. And if there is, then we can rethink our evaluation on the data. So the first one I'm going to do is our Pearson's, and that's the simple one to do. So we just use our Correl function, come down and select our two data arrays that we started with. First the length data, and then our width data. Close the brackets and press enter. So this is our R value as calculated by Pearson's. So I'm just going to change our title here from correlation to Pearson's. Next, I'll calculate the Spearman's. I'll put this in the cell over here. So the first thing we need to do is just calculate our rank for each of our data sets. So this is going to be the rank for our length, and this one here will be the rank for our width. So as in the previous example, again, it's just the rank average. Choose our number that we want to look at. Choose our data set we want to compare that value to. Close the brackets and just make sure we lock the correct cells for when we drag it down. And then do the same for the width. Again, just making sure that we lock our range of cells, so when we drag down, they don't move. Now we have our ranked data, we can come back to our cell in the corner here, and just type in our Correl function again. This time selecting our ranked data. We now have our Spearman rank, R value. And as you can see, the actual difference between our Pearson's value and our Spearman's rank value here is very, very minimal. So in this edge case where we're almost normalized data, but not fully normalized, we could possibly use the Pearson's over the Spearman's, and vice versa. The next thing to do is calculate our t-stat value for both our Pearson's and our Spearman's, and then our p-values for each of those. And that's what we'll use to compare. Now, again, I'm just going to do this off the video, so it's going to magically appear in front of you. As you can see, I've now calculated the t-stat and the p-value for both our Pearson's R values and our Spearman rank value. The first thing you'll notice is the p-value is incredibly small. It is well below the 0.05 threshold that we set to say whether our R value is significant or not significant. In this case, our p-value is telling us that the positive correlation that we are seeing in both cases is highly significant and can be trusted. So our data is well correlated. So even in this example, where we've got data that is showing very good results, we were still guessing a little bit at the start on whether to use the Pearson's or the Spearman's rank. And this was with the help of our two histograms. So is there a way that we can improve our visual representation of the data and somehow overlay something on these histograms that will tell us one way or the other whether our data is fitting a normal pattern? And in Excel we can, it's just a little tricky. And this is where something called combination charts come in. This allows us to overlay a second graph on top of a pre-existing graph. Now the graph we want to create for overlay is something that's called the probability distribution function, or PDF curve. And this is simply a normal distribution curve that's created from the mean and standard deviation from each of our data sets. So I'll go through and just demonstrate how we do this. The first thing we want to do is calculate the standard deviation and the mean for each data set. So I'm just going to add some more columns to this little table at the top here. The first one will be our mean, and the second one will be our standard deviation. I'm just going to format that table. There we go. So the mean is easy enough. We just go to our average function and then select our full data set for our length and just close the brackets. And I can just drag that to the right and get our mean for our width column as well. Now the standard deviation is using the sdev.s. So select that, select our length dataset again. We can close our brackets, press enter, and we've got the standard deviation for that dataset. And again, I can just drag this across one column, and it's now picking up the data for our width. So once we've calculated those two, we then need to create a new set of data, which we can use for plotting. And these should take the form of XY coordinates. Now I'm just going to start a new table down here to work out our X and Y coordinates for our length data. So I'm going to start a new table. It's going to be X and Y. I'm just going to put some formatting on that. Now in terms of the number of X coordinates we want at least the same number as we have bins. Now if you're dealing with histograms, the easiest thing to actually do is copy across your bin number. You can then drag this down. In our case we had 10 bins as such. So we now have our X values. We now need to work out our Y value. This is where our normal distribution function comes in. And in Excel, you can get to this by typing norm followed by .dis. And this will take an X value, in this case our bin value, the mean value we calculated earlier, and the standard deviation we calculated earlier. Now the last thing it's asking for is do we want to create a cumulative distribution function or a probability mass function? Now we're interested in the probability. So what we want to do is select the bottom of these options, the false, and enter that into our function. We can then close the brackets and press enter. We now have our Y coordinate for our normally distributed data at point X. Now to drag this down, I just need to lock some of these cells. In particular, I need to lock the G7, which is our mean, and our G8, which is our standard deviation. Once I'm happy, press enter, and I can drag these down. Once we've calculated our XY coordinates, the next thing to think about is how do we get our XY coordinates plotted on our pre-existing histogram? Well, this is quite simple, but it does require several steps. The first thing to do is come up to our histogram and select our Select Data widget. What we want to do is add our Y coordinates from down here as a new series. So we go to add. Now for series name, I'm just going to call this PDF, so probability distribution function. And for series values, I'm going to come down and just select our newly calculated Y values and say OK. Now, as you can see on our graph over here, our new series is appearing, but it's appearing as a set of new bars on our bar chart. At this stage, this is fine. We're going to change how it looks in a little bit. So we say OK. The next thing we need to do is tell our graph that we want to have our new series, which is in orange, plotted not as bars, but as a line or a scatter plot. So what we do is we right click and we come down to change chart type. Now, as you can see, we are on our column chart type or bar chart. That's not what we want now. What we want to do is come right down to the bottom where it says combo. If we click this, we get a lot more options on how we display our individual series. Currently, our frequency series, which is our histogram data, is being shown as a clustered column. This is correct. This is what we had before. Our probability distribution function data, down here in orange, is now being shown as a line chart. This we don't want. So we want to actually change that to a scatter plot. So we come down to our XY scatter plot and we choose the XY scatter plot with curved or smoothed lines. Having straight lines between it isn't really going to work. So choose a smooth lined scatter plot. As you can see on our little preview window here, we now have our probability distribution function plotted with a smooth line. But it is at the wrong scale. So our vertical scale for our histogram is a lot larger than our vertical scale for our probability distribution function. So how do we solve that? Well, this is quite simple. What we need to do is come down to where it says secondary axis on this little widget and tick the box for the probability distribution function. And this will rescale that particular line chart or scatter plot to the correct vertical scale. We can now say OK. This will update our chart in our worksheet with our now correctly plotted probability distribution function. We can see visually whether our data in our histogram is following this pattern. And this is how we create combination charts. The final thing I'd like to show you is just a quick visual trick that we can use with combo charts to improve their appearance. If we look at our length combo chart that we've just created, you can see that we now have two axes in the vertical direction. The one on the left here is our frequency axis, and the one on the right is the one associated with the probability distribution function. Now there are situations where you may only want to have one of these axes visible. For instance, you may only want to have your frequency value axes showing and hide the probability distribution function axes. So how in Excel do we do this? We can't just click on this secondary axis and press delete. This will muck up our newly created combo chart. What we have to do is right click, come down to our format axes option. In our little widget here, we select text option, and we want to come down to where it says color, and this is changing the color of the text. And we just choose the same color text as our current background, in this case white on white. And as you can see, this visually masks our text. The next thing we might want to consider is reducing the amount of now white space we have on our right hand side. And we can do this by changing the size of the font that this axis is printed in. And we do this by coming up to our Home tab on the ribbon menu, come to our text and font size option, and here I'm just going to type 1 in and press enter. As you can see on our chart, we've now visually shrunk that axis. So if we click off our chart, it now looks like we don't have a second axis on this right hand side.